university. I feel I'm a bit outside this conference because my topic is nothing to do with PPO or the viscosity or cohesion, but it's just as a model, simple model for maybe progress or variability. So our model is a non-standard type description, so no hydrodynamics, and non-standard type cohesion. It's not a class mechanical like this. And our hope is to make a simple model which can well reproduce the basic observational features of variability. And final goal will be to get a good physical insight into underlying physics of lateral variability. Okay, as you know, this is the characteristics of lateral variability. In the case of senior state 1, and this is X-ray testing light bulb, it's taken by a long time ago. It's a Ginga satellite in Japan. And this is part spectral density, as you know. Part spectral density shows 1 over F-type fluctuation spectra at high Fourier frequencies. So this is what we want to reproduce by a simple model. So maybe a few decades ago, there was some discussion if the black hole variability is chaos or not. So there are some analysis made based on the notion of chaos, but the analysis of X-ray light clouds, for example, and some reported the presence of low dimensional, so 4, 5, or 6 dimensional chaos. But the big problem is so what physics can get. So if there's for instance, if there's a 5 dimension, what does it mean? So instead, we take a slightly different approach. As you know, there are many things show the fractal. So fractal and parallel. These are very ubiquitous, not only in the astrophysical context, but in the nature itself. And in addition, we found many good examples of 1 over F-type fluctuations. But in other words, we can say that the fractal means the spatial cell similarity, or the 1 over F fluctuation in the temporal cell similarity, because changing of time scale, length scale, we have similar patterns. So these should be somehow related. So also there should be some mechanism which may be responsible for producing fractal, parallel, and 1 over F fluctuations. And sometimes it's called that these are all characteristics of HOK. It's not a case. So just show this graph. And usually time-dependent behavior. Simplest case is a harmonic oscillator. That shows the sinusoidal oscillation. So it's a pure periodic. And chaos means that somehow it's characterized by the exponential growth. As you know, the slight deviation grows exponentially in time. But just in between the periodic and chaotic behavior, there's some region which shows parallel distribution. It's not the sinusoidal, it's not exponential, but parallel. So there's some hope to produce this kind of phenomena in the context of equationism. So here we pay attention to a specific model which is called self-ordinate criticality. This is developed in the field of nonlinear dynamics. So let me explain next what self-ordinate criticality means. Okay, this notion was proposed about 2 decades ago by Bark et al. This is the basic notion which relate spatial fractals and temporal 1 over F to beta type fluctuations. This notion is about a good metaphor with a sandpile model. So namely, suppose there's a table, we have a sand particle 1 by 1 from the above. And eventually, so we put much particle one after another. And eventually, that sand particle will make a pile. And so here we observe that if the slope of the pile is a critical number, then the particle in the upper layer will slip down because and produces avalanches. Sometimes this kind of avalanche is large scale, sometimes it's small scale. So we expect very frequent occurrence of small-scale avalanche, and sometimes have bigger size avalanche. So that produces a so-called parallel or fractal size distribution. Size means the size of the area which undergoes avalanche. So we expect this fractal size distribution, and also if you count the total energy dissipated in this process, we expect to have 1 over f to the beta type temporal fluctuation. And this is a very simple model, but it is very powerful model. And this model can be applied to many other systems which show fractal or 1 over f type fluctuation. And good examples are earthquakes, Newton's gravity, the forest fire, and many things. So now we are considering and applying this model to our case. So in the original model, it's a sandpile model. We just make it upside down. And okay, so this black hole here, and there's a mass input here, and eventually it's slide down. But if this slope exceeds some critical number, it goes down. So this is our idea. Yes. This is very reminiscent of some kind of insect which is found in the temples in Japan. But maybe you don't know. In the temples, for instance, if you visit the temples in Kyoto, you just see the ground under the big hole. Then sometimes there's a small insect like this and have a good nest. So this insect is waiting for here. So until the ant happen to slide down to this net. So this is a good example. Maybe this kind of things can be understood only by Japanese. You never have this insect. Okay, so the procedure is very simple. Here I first show the original model. Next, I present the revised model. So let me first explain the original model. It's a very simple model. This is a detailed automaton rule. We divided this plane into numerous cells, and we have 2 rules. And one is if the mass of the cell, also the CLF, and cell exceeds a critical number. So we define the mass as a particle cell. So Mij means the mass of the this cell, I and J cell. If this mass exceeds a critical number, we get avalanche, and the mass of M going this way, so in the inner side. And in addition, we introduce some diffusion, small diffusion index, and calculate the Mineshige according to this formula. And delta M is accreted mass. Then repeat this process many times, more than 100,000 times. Then we can get a good fluctuation light curve. So this is a simulation movie. This is this plane, and this is disk mass, and this is a plot. The black spot is released. This is a movie with released energy. So you have some flaring effect, and showing some rapid rotation. Yeah, here we assume Keplerian rotation, and occasionally we have big flare and small flare and many flares. And this is light curve. Sometimes, so it all happens that the small flare occurs, but occasionally you have a bigger flare, and then have the maximum this kind of flares. So sometimes have a big flare, sometimes low flares. So in this way, it's a very simple model, but we can create 1 over f type fluctuation. As you see, this is not periodicity. There's no periodic variation. It's just random fluctuation. But we have good variety of flare amplitude. So
I will make, sorry, irrelevant comment. Many of you probably now see what SOC means. It is Scientific Organizing Committee or Self-Organized Activity. This is how we work when organizing conferences. Sorry.
So this curve was it m dot or the energy release?
Not the energy release.
Yeah. So it's integrated over all radii, and most of it comes from the inner part.
Yes, according to this.
Oh, I see.
So it's more biased in the mass accretion in inner. Okay, so this is simple. But the big problem, okay, and that model. I like that model, and it's very interesting, but nevertheless, it has a shortcoming. That means there's no physics there. So we need to think about what physical mechanism produces fluctuation and dissipation. So a good example, so we focus on MHD, so-called induction equation. So induction equation describes how magnetic fields evolve with time. And basically have two terms, and time evolution B is described as two terms. One is the dissipation, and mainly due to the magnetic reconnection. So if the magnetic energy piles up at a certain place, it's released due to the magnetic reconnection. That's the first term. And the second term is that can be described by this form. So if there's a motion, V is a gas motion, if there's a motion which produces a fluctuation in B field. So this reflects the fluctuation due to gas motion. It's a combination of two things. And one is the fluctuation, B field, and the second one is the dissipation of energy when certain conditions met. So we can describe the evolution of B field in many different places for in time-dependent fashions. So here we simulate evolution of magnetic fields. And actually, this kind of idea has already been proposed for the explanation of solar flares. Okay, solar flares have long known to show the so-called parallel distribution, parallel flux and duration distribution. So by the X-ray observation, soft X-ray observation, they show the actually peak intensity of flare and average intensity of flare of uniform parallel size distribution. But in addition, we also analyze time light curves, soft X-ray light curves of the sun. We find that the sun can 1/f fluctuation. This is the result, and this is the frequency, and this is the burst intensity. We have something like 1/f to 1.5 fluctuation spectrum. So it's very similar to what we observe in the macro cases. For reference, this is a Cygnus X1 PSD. So you have similar profile. So again, so in this model is essence already SOC model for the solar flare has been proposed by Lou Hamilton in 1991. Unfortunately, he already quit astronomy, and now he becomes an astronaut. So he has a good selection. Again, so fluctuation and dissipation of magnetic field with local interaction. This is very important. Local interaction is if dissipation occurs, magnetic energy dissipates, and magnetic field will also diffuse away. So fluctuation, combination of fluctuation, dissipation, local interaction produce parallel distribution. And essence, again, can be represented by this induction equation. So we do the same thing, but in the context of equation. So this is a revised model. I'm sorry, there's no viscosity in this. No viscosity, no hydrodynamics, but just a simple model. Again, we divided this plane into many cells. At random fluctuation on quantity B, B is start from the magnetic strength at each side. So first we put fluctuation, depict these terms at every time step, at every cell. And then we calculate the number squared B, and if this value exceeds a critical number, then let an avalanche occurs. This is, so then the energy is dissipated. So the accumulated magnetic field energy is dissipated, so that's the assumption. And then we let all the variables in this by hand. So this is represent for the equation. And calculate the luminosity in the two different ways. One is the proportional to the B square, and the other is proportional to this is dissipated energy. And we repeated this process more than 100,000 times. Before presenting our result, let us review again the characteristics of observation of the series X1 light curves. And this is X-ray intensity, as well as mentioned, and this is time, and this X-ray curves, and this is power spectral density, log F to the PSD. And in addition, one more figure here. This is recently reported flux distribution. And actually, flux distribution shows before log normal distribution. This is a linear scale. If you make a log flux, then you have a Gaussian profile. So these three things are very on the basic properties of light curves of series X1. So we could basically reproduce these things by our simulations. And this is X-ray intensity. You have some flare light curve like this. And power spectral density, in this case, of course, there are some model parameters. But so this power slope is somewhat depends on some parameter, but the value is something like 1 to the 1.7 or 1.5 is. So again, so it's a log plot in the flat top profile at low frequency and power at decline at high frequency. And in addition, we could also reproduce a log normal distribution like this. And this is the luminosity, and this is the frequency of the flare events. So these are results. And let me finally show the parameter dependence delta. This is a parameter delta denotes the mean fluctuation amplitude. So in our simulations, we put the perturbation in the B field. So the average of input perturbation is treated as a parameter. For the smaller perturbation, we have this kind of, like AGA light curves. We have some mean, we have a fluctuating in the up and down this way. But if we increase this fluctuation amplitude, we have minor this kind of light curves. It's more like solar flares. Usually the luminous level is low, but occasionally have a big flare like this. And the case of 0.75 is just an intermediate. So by changing this parameter, we can make a variety of light curves. But all of them commonly show 1/f type fluctuation spectrum and log normal flux distribution. Okay, summary and feature issue. So observations show rather complex time variations. But here I demonstrated the basic observation feature can well be reproduced by a simple serial automata model. And the success of our model indicates man-field fluctuation being the origin of variability. Of course, this is not proof. This is just a conjecture. So the fluctuation, the coupling, combination of fluctuation with dissipation with local interaction will produce fractal or parallel distribution structure and 1/f type fluctuation. And of course, this is a toy model, very simple model, and we need to consider many things to make this model more realistic. For instance, so far I totally neglect the hydrodynamic part. I only consider the induction equation of fields, so consideration of hydro parts of equation are necessary. And what is more interesting is to make a direct comparison with the numerics and MAT simulation, which we have not done yet. And if this is really occurs, then we have some signature of this kind of avalanche effects in the simulation data. And of course, and this model cannot produce QPOs because there's no characteristic frequencies. So for the spectral variability, original QPOs left as a feature. Okay, that's all. Thank you very much.
Władek, Amel, Kristen.
Yeah, you go first.
Okay, Władek first, Amel, then Kristen, then and others.
I think I saw a power of 1.7 and you're results. Is this universal or is this?
Oh, it depends on the model. Sometimes we have 1.4, sometimes 1.9, but generally between the 1 and 2.
Thank you.
And let me add that, that if it is a model of accretion disk, then this power will be changed with inclination. So if intrinsically it is 1.7, you make an inclination and it would be a different power in these models.
Yes, and in this model it's totally Newtonian. If you consider relativistic, it's much different. But the block is rotating at high speed. Then this powers will change, which molecule is shown. So some changes in the power, but cannot be greater than 2 or less than 1.
So, am I right in thinking that these SOC models, this existence of this critical threshold above which you suddenly have an analog, that's crucial for these models.
Yeah.
So now in this MHD version, you have this critical threshold in del squared V, I guess. So in an effort to try again to connect this with the physics that we think is going on, do you know of any plasma instabilities or something that do require a threshold or a del squared V or curl J or something?
I don't know exactly, but some indication for the case of solar flare. I probably is the solar ellipses, like Professor Shirato, then they made some model. So, the model for the condition to produce the solar flares, big flares. They found something like this, but it's not exactly the same. So we need to elaborate that part.
Okay.
Yeah.
But they do have. But it is the same threshold that they find that the solar flares also.
Not the same.
Show.
Yeah, if you interpret his result, yes, same, but it's not direct concept. Actually, he said it's more important is drift velocity, which produces the magnetic reconnection. So drift velocity is related to the delta and level of KB. So it's something related.
I see, but
it's
so it's not
one-to-one.
gradients in J then, but
Yes.
Please tell.
So you start with this model with this sort of with an accretion unity arguments, like getting closer, deeper in the potential.
Okay,
so you have this advection of the massive particle.
Yes.
Then you do with the magnetic field, and you also have this advection of the magnetic field.
Yes,
in this model.
yeah, by hand.
Right. I was curious about how critical is that. It seems it may be critical, but I want to understand how critical is that for the model in the sense that if you think of a corona on top of an accretion disk, what I think physically is relevant is that you might dunk energy sporadically, and it's not clear to me that the notion of advection has anything to do with what's going on.
You're right. Yeah, you're right. In this
so
model,
how critical is this advection in your model to the properties you get?
Oh, in this model, you're right. That's and advection motion has never been important.
Because
However,
of the sand pile effect, is it?
Yeah. Oh, the fluctuation occurs at any place. But the big problem is, okay, so if you dissipate energy, eventually you have no material. So we put more material. Okay.
Oh, so it's a source term, I see.
The source term, yes. So we need to assume, okay, so source term is a gravitational energy. So that means, so I said that by hand we get one field is actually magnetized plasma get in to get the energy.
But if
that energy goes to the magnetic
right,
field.
if you can get that in the solar corona, there is
No,
no
no,
notion of advection there, actually. And you could say,
yes. So to produce this kind of feature, then advection accretion is never been. It's never. So at any time, its reflection is sort of reflected. Then accretion this is happens, but that's the additional thing, and it's not essential in this model. So that are interpretation.
Good. Now, You? No. Axel.
Could you change the radial angular velocity gradient, which is Keplerian at the moment?
Yes, yes.
If you change that,
Doesn't
would, it would not matter?
doesn't matter.
Uh-huh.
The original model we assumed no rotation.
Yes.
Here we assume the Kepler rotation. It doesn't matter. This index may change by 1.1 or 0.2,
Yes.
but the general feature doesn't change.
And if you were to do power spectra, spatial power spectra in the phi direction, would you see power law scaling there from the model?
We have not yet checked. Oh, that's good. Yeah, question. We have not checked it in the phi direction.
I mean, you would. I mean, that's probably the closest that you would get to making contact with turbulence, unless you change the model further. And you would, perhaps. There's no reason why you should not expect the cascade-like behavior in that, which is easiest to see, of course, in the phi direction, because that's periodic, and then you can do power spectra in the phi direction.
Okay, thank you. Oh yeah, we consider the point. So far, I never.
Yes. Here.
Are there any prediction about the collision? It means larger flare occurs in the inner part or smaller one occurs at the part?
Oh, usually larger means on the almost large area of the accretion disk is involved. Then that large flare. Small means only small scale average. So it depends on the area of the accretion disk which undergo the average.
Not depending on the radius.
Some dependence on radius because the energy is more preferentially produced in the innermost part. So there's some bias in the innermost part. But there's phenomenologically, the average at any radius, and to have a big flare, we have a large scale average.
Anybody else? Okay, thank you very much.
Okay, thank you very much.